Hello and welcome to our lesson on the combination of transformations for logarithmic functions. Last day we talked about being able to put different numbers into our logarithmic base 10 equation and have very predictable effects. If we go right back to general function notation, we talked about the fact that we could have multiplication factors either outside in front of our function or inside our function, right in with x. We could add or subtract inside or outside of our function as well. We mentioned that the multiplication factors caused expansions and compressions. The addition and subtraction factors caused shifts, either vertical or horizontal. We could, if we wanted to put a 2 out front or perhaps a 3, 4, and 5, subtracting inside the bracket and adding outside the bracket, if we were to put those into our logarithmic equation, we would have a 2 as a multiplication factor in front of our log function of base 10, a 3 inside, a 4 in for h, and it doesn't matter what letters you use in the equation. Different textbooks will use different letters. You'll often see a k in here or perhaps back here, but it's the location of the number inside the equation that has the predictable transformation. We talked about the fact that multiplication factors were expansions and compressions. We didn't actually write down about the idea that anything that happens inside our function, inside with x, and that would be inside the logarithmic argument, that would cause horizontal transformations. And our horizontal coordinate for any function is our x coordinate. And so these change the x, the horizontal distance of your curve. When we are talking about putting numbers in front as a multiplication factor or after our function, so outside of our logarithmic function, it would be this multiplication of 2 out front or this addition of 5 out back. These are vertical transformations, a vertical expansion by 2, a vertical shift up by 5. And opposite to our horizontal, they affect the horizontal coordinate. Our vertical transformations change the y coordinate. Now last day I asked you to do some transformations of logarithmic functions where we only had 1 or 2 numbers in any of the questions that we had looked at. And if you were looking to see whether you were graphing correctly, then you could make use of Desmos on our graphing software, or you could go to www.desmos.com or check our classroom website, because I do have a scan of the solutions from last night's homework as well. What we want to talk about today, because I am betting that most of you graphed those visually. If you only had a couple of fairly easy numbers in your equation, you could visually move your base graph dots around. What I want to talk about today is a chance to be successful when the transformations get crazy. Either we've got all 4 numbers in a logarithmic equation, or those numbers are fractional, or it's just not as easy perhaps to do it visually. Now I know some of you are very talented visual graphers, and I'm not here to change the way you transform a function. On a unit test, if you want to use a visual method always, even when it does get with crazy numbers, that's fine. I don't care how you land your curve. I just want it to be landed in the right position. But I do feel it's valuable to learn both methods, and so I would ask you to do the next homework tonight with this calculation method. Where did my transform dots go? So if we take a look at this paragraph here, it gives us the transformational information to be able to create an equation. The logarithmic function, our base graph log 10, has been vertically compressed by a factor of 2/3. That would be a multiplication factor in front, and so my new curve, my transformed curve, would have a 2/3 out front of my logarithmic function. It has been horizontally expanded by a factor of 2. Now, we do know that to have a horizontal expansion, we're going to be dividing by this d value. I have an a value out front of a 2/3. That's my a value that went in as a vertical expansion, or this one is a compression because it's less than 1. Our d value here, if we identify that variable, is a half, because horizontal always does the opposite. We'll actually be dividing our horizontal x coordinate by whatever d is sitting in our equation. It then says it's horizontally translated so that the vertical asymptote is at -5. Now, if you remember, all of our logarithmic base graphs had its vertical asymptote on the x equals 0 mark. And if it was to be moved then to an x of -5, and we may as well put it in there, then that means that there was a transformation that went left by 5. While I'm here, I may as well draw my base 10 logarithmic base graph. Over 10 up 1, over 1 up nothing, over a 10th down 1 are the 3 coordinates that we need. And nice smooth curve through there. That would be our f at x is equal to just log base 10 of x. And so we know that in our transformed function, we have to have an x that goes left by 5. Now, when I put it in like this, it is not going left by 5, because we have this multiplication effect that is directly connected with our x. And so what I want to do is hold my x special. Now it's left by 5, and then that multiplication effect can be held special away from the x. And what else do we have here? Vertically translated down by 3. So a 3 afterwards. Write an equation of the transform function and state its domain and range. Now, by the time we get to a unit test, we should be able to state the domain and range right from our equation. And so what I want you to think about is domain is the permissible set of input values. It essentially asks how far left or right does our curve go. Now, a logarithmic base graph, all of the inputs have to go into the argument, and our argument needs to be a positive value. And so all of the permissible inputs are the positive x's that are on anything bigger than 0. But that's not going to be the case for a transformed function. First of all, we know that we have moved left by 5. Did we have a reflection in this that I'm forgetting? Oh, yep, absolutely. Reflected in the y-axis. So we had our asymptote going to a -5. That was a left by 5. That's definitely going to affect the domain. And reflected in the y-axis, I have a negative in here in my horizontal. Any of the horizontal effects will change the domain, the horizontalness of your function. Now, we are going to take our base graph, reflect it over the y-axis, and then move it left. We always do the transformations, as Bedmis would ask us to do the multiplication factors first before the shifts, up, down, left, right. So we would do that multiplication of the negative over the y-axis, shift everything to the left, and so our curve is going to be in this area here. It's going to be everything under that 5. And so let's graph it, and then we'll write our domain afterwards. And then if we think about what affects the range is how far up and down this graph goes. Well, it's all real numbers. It goes down, everything goes down to -infinity, and it rises slowly, but it always continually rises. And so our y values will be calculating out all the way up to +infinity. So let's not forget to do that, but I want to be sure of it after we have graphed it, so our domain and range. So let's get our base graph dots. It's over 10, up 1, over 1, up nothing, over a 10th, down 1. Those are the numbers that would easily go into a y is equal to log base 10 of x. If I put a 10 here, what exponent do I need on a 10 to get a 10? It would be 1. What exponent do I need on a 10 to get a 1? that would be 0. And if I put a 1/10 here, what exponent would I need on a 10 to get a 1/10? It would be -1. Now, here's where we can get to the point where you choose to graph it visually or you choose to graph it with this calculation method. When we want to calculate the image position of where our original base graph dots go, we take our horizontal coordinate and we are going to divide it by whatever D is sitting in this location. So our X divided by D. Horizontal always does the opposite, and so it divides instead of multiplies by this half. It doesn't become half as big, it actually becomes twice as big horizontally with this value in here. Our vertical coordinate, our y coordinate, is going to be affected by the vertical transformation. Specifically here, we're going to be taking 2/3 of our vertical values. And so our a value is always going to multiply our vertical coordinate. Now, if I take my x coordinates and I divide by my d, which is a -1/2, then I will have a -1/2 as a fraction under there, and then we know that we never divide by a fraction, we invert and multiply, and so I will have all of my x coordinates being multiplied by a -2. And so let's go down there, we have -20, -2, and we would have -2/10 or a -1/5. And my a values being multiplied by 2/3 of what they were. And so 2/3 of 1 would be 2/3. 2/3 of nothing would still be nothing. And 2/3 of -1 is going to be -2/3. Okay, now those are the positions of my base graph dots with only the multiplication factors applied to them. Now I could calculate the very end position of my dots. I know I'm needing to go left by 5, and if I want to take a horizontal coordinate and have it go left by 5, I would need to subtract 5 from every one of these. Similarly, in order to go down by 3, that's a vertical coordinate that would need to be subtracting 3. And so I totally could find the resting end position. But I find a combination of calculating and shifting. I just remember once I've calculated the expansion and compression effects, then I will just shift everything left by 5 and down by 3, and I will dance those dots to where they need to go. So we start out with our -20 right there, and -20 and 2/3, so about there, and we need to go left by 5, 1, 2, 3, 4, 5, and down by 3, 1, 2, 3. Then I have my -2 and 0, and so I'll start at my -2 and 0, go left by 5, 1, 2, 3, 4, 5, down by 3, and plant that there. And finally, my final base graph dots, -1/5, so maybe about there, and down 2/3, so about there, and I need to go left by 5, 1, 2, 3, 4, 5, 1, 2, 3. I know that I'm going to approach but never meet the value of my asymptote, and then a nice smooth curve through the rest of the dots here. And that, well, careful that you don't do exactly what I just did. Notice my line went up and then down a little bit. That actually is not accurate as to whether the representation of all the million billion dots. I mean, if I put a -16 into my equation, -16 plus 5 would be -11 times a -1/2. Take the log, do that multiplication, I would get the representation of where that dot goes. It doesn't come up and then back down. It's a nice smooth set of dots in between there in a linear manner. So be careful, don't get lazy with your graphing. And this one, I guess we were in function notation. We should probably stay in function notation. 2/3 log 10 of -1/2. And if you have more than one line on a graph, you must label them. So there is our transformed graph from our log base 10 graph with all of these crazy transformations. Again, if you can graph it visually and get it there, perfect. On a unit test, I will never require you to do this, but it's a very valuable skill, either to double check or to use it in the specific case of having very involved transformations. It's also really important to be able to, if I gave you, hey, I've got this log graph and I want to know where this particular dot went given this equation. That would be a fair game question on our tests as well. Down here in the bottom, we have some also typical test questions and describing transformations. Remember, when we have our shifting left-right, we may not read, this is not going left by 10. We can't read the left-right unless we have factored away our d value. And so, factoring away this d value, if I divide it out of this piece, I will be just with a single x. And if I divide my -2 out of here, this curve is actually going right by 5. And so don't be lazy with your terminology when you are stating transformations. You want to, with a reflection, this one has 2 reflections, you want to explain which axis you're reflecting over. So this one is a reflection in both the x-axis and the y-axis, y-axes. Okay, we have a 3 out front, and so that is a vertical expansion by 3, by a factor of 3. A 2 inside here, remember our 2 is going to be dividing all of our horizontal values, and so that will be a horizontal compression by a factor of 2, or 2, half of what it was. And then finally we have a -5 inside my function, and so that is a horizontal translation or shift, horizontal shift, right by 5. Okay. Similarly, creating equations, state the equation that results when f at x is equal to log base 10 has been vertically compressed by a third. So our a value out front is a third, reflected on the y-axis. So again, we have a negative as a d value, horizontally translated 10 units to the right. Don't do this. That is not going right, believe it or not. If you punch this into a graphing calculator, it would be going to the left, because if you factored out this -1, factored it out of here, and factored it out of here, it would leave a +10. And so in order to have it going to the right, we need to hold that d value factored away from our x inside the logarithmic argument. State the equation that results when you've got a log graph been vertically expanded by 2. So we have a 3 out front, horizontally compressed by 2. So our d value, we would need to have a 2 here, because x divided by 2 would take all of your x's and take half of them. Compressed by a factor of 2, reflected on the x-axis. So our a value is negative. Vertically translated up by 4. So I don't have a horizontal left-right, no adding or subtracting inside the logarithmic argument, but a +4 afterwards. And we discussed last day that that 4 will sometimes be shown out front. So if you see something like this, then know that they've chosen not to put the 4 in back, they've chosen to put it out front. It is still a shift up by 4. Okay, so at this point, what we need to do is to take a peek at graphing from a logarithmic equation. Again, we can't read the left-right until we factor this 2 away. We are not going left by 8 here. And so we have a 2x plus 4, if we factor it out of both of those spots, then a +3. We were asked to state the transformations, and so at this point what I'm going to ask you to do is to give this a whirl on your own, and we'll come back to the video, so perhaps press pause on the video here and give this a try. We're going to, it didn't actually explicitly say to draw the base graph, but let's draw the base graph over here, log base 10, and then draw the transformed graph, and down here calculate the x and y intercepts. And so pause it, give that a whirl, and then come back to the video and I'll show you the solutions. All right, hopefully you've been successful at stating the transformations. A reflection in the x-axis with an a value of -1 out here. Horizontal compression to a half of what it was. Horizontal shift left by 4. And a vertical shift up by 3. Your logarithmic base graph should have over 10 up 1, and then over 1 up nothing. Over a 10th down 1 is pretty hard to show accurately, but just do your best there. Now, I'm hoping that you gave this a whirl using the method of calculating where the dots go. Your x divided by d means that you are going to be taking every x and dividing by 2. So 10 divided by 2, 1 divided by 2, a 10th divided by 2. When you do that, you'll be inverting and multiplying that 2. A 10th multiplied by half is a 20th. And so over 20th. And our a value was a -1. And so we're going to multiply all of our vertical values by a -1. And then take everything left 4 and up 3. When we do that, we get this logarithmic base graph. Our domain, oh my goodness, we forgot on the last one to put in the domain and range, but we talked enough about it. Hopefully that was, it's enough to do it here. Our x values have to be greater than -4. Here, they have to be greater than -4. Over here, on the front, everything was less than a -5 for our domain. The range was still all real numbers. Similarly here, the range is all real numbers. That'll never change for a logarithmic base graph. You can't do a transformation to a log graph that changes that unless it's an inverse, because then we saw the inverse of a log is an exponential. Now, calculating the x and y intercepts. Remember, your x-intercept, you want to have a dot on the x-axis. You do not want to have a y value. You don't want to go up or down, so your y needs to be 0. When we have a y value of 0, we put the 0 here, and we need to solve for our x values. So we'll subtract 3 from both sides, and we get a logarithm. Oh, it's still negative, so we'll divide away that -1. And now we just get a logarithm equals a number. At that point, we go to exponential. Base 10, exponent 3 is equal to the 2x plus 8. That's 1,000. And so we subtract the 8 and divide by 2, and we get 496. Our x-intercept at 496. And the reason for that is this line is decreasing, but it takes a very long time to decrease enough to be crossing your x-intercept. So way over at x of 496 will you get your up nothing. This one's easier, finding a y-intercept, subbing in 0 into our logarithmic argument. So we get 0 plus 8, log of 8, that's negative plus 3, gets you about a 2.1. And so we'll go back to our graph. And yep, sure enough, that looks like it's just above the 2 mark where we are crossing, where we get a x coordinate of 0. And very often when you are on a test question, if you calculate your x and y intercepts and you look at your graph and go, that doesn't make any sense, then you can sleuth out your error, because you either have an error in your calculations or more probably you have an error in terms of where you transformed your graph. So hopefully that gives you a good start on transforming really crazy logarithmic graphs. I have provided you with 4 different equations to be successful in terms of combinations. Please employ this calculation method to practice that on all 4 of those graphs. And then some practice either decoding transformations from a equation, or given these different transformations, creating the equation of the line. Down here, I'm starting with general function notation. If you applied this general function notation to this log graph, now notice it's not a base 10. Our curriculum doesn't have us graphing more than base 10, but we can certainly write equations of more than base 10. And you'll notice here that we had some different logarithmic bases as well. So use the log base graph that is suggested in each question, and the general function notation. Place the numbers into the curve in the right position, and then state their transformations. And all of these are have their solutions on our website as well. So please be checking our classroom website for the answers, and checking to see whether your graphing is going well as well. Thanks so much, and we'll see you tomorrow. Bye, guys.